Yes, good afternoon. Moses, just switch on your mic if you're there and confirm to me that you can hear me.
Yes, good afternoon. We can hear you, sir.
Okay, thank you. So today I waited for you people for 10 minutes. So let's continue with what we were doing in the previous class. Moses, hope you can see the presentation.
Yes.
Okay. So we're considering the series regulator, the series DC regulator. And this is the most common configuration. We have your unregulated input, V1. We have your reference element that gives us a value Vz, where Vz is the rating of that particular zener. You got your error amplifier, and then you got your series element or series control element, which typically comprises of two transistors. In the last class, went into detail as to why we use two transistors. The reason is that most op-amps tend to have a limited current drive capability. So for example, if the maximum current capability of the particular op-amp is 10, let's say 10 milliamps, and you want to supply, say, 10 amps to the load, so it means this 10 milliamps must go through this second transistor called Q2. So if the gain of that transistor is, say, 50, then at its emitter, we'll get approximately 50 times 10, which is half an amp or 500 milliamps. And then that half an amp will be amplified again by this Q1. So most of these output transistors, they're normally power transistors, which are connected to a heatsink, and their gains are normally quite low, maybe 20. So if you've got half an amp coming at the base, half an amp times 20 will be 10 amps. But if your design problem was to design a power supply with 20 amps, and you had the same op-amp, same transistors, then you'll find it will not be possible. You'll have to look for transistors with higher gain. Somebody's trying to come in again, I don't know. This Awino guy always likes coming late and discovering the class. Okay. So next, we've already derived the working equations. So the design requirements is what we were considering last time, which we did in detail. We went to the data sheet of a particular manufacturer. Now, in such a circuit, the DC power delivered to the regulator by the unregulated power supply can be written as, we can call it power in is unregulated power times the current in. So like if I was to maybe draw our regulator here, and this is our load. And this is your unregulated power supply. And this is VL. So this is your unregulated. And this is your regulated. And this is your regulator. So Pin is the power going inside, and this will just be V1 if the current coming here will be the same current going out. This IL, actually in the circuit there will be a slight apart from maybe the current going to the op-amp, which is actually negligible, so we can neglect it. So Pin would be V1 into IL, and power going to the load will be VL IL. So I've just written it here on the left-hand side. Pin is unregulated voltage times the load current, and the power to the load, we're calling it PL, would be the regulated voltage, which is your VL now, into IL. And therefore, the difference in power, which is going in, and the power which is going to the load must be the power dissipated by our regulator. I'm calling it PD. This is your dissipated power. By the regulator, the dissipated power by the regulator. In design, normally we want the power dissipated by the regulator to be as small as possible, because any dissipated power there means a lot of heat is being generated. A lot of heat is being generated. Power is expensive. A lot of heat being dissipated also means that the life of the semiconductors are going to be less. Okay, normally we use things like electrolytic capacitors to smoothen the power. Also, those ones consume some energy. And when they heat up, they lose the electrolyte. So the life of your regulator tends to decrease. So we want power dissipated normally by regulator to be as small as possible. So we can write an equation that the power dissipated in a series regulator, which I'm calling PD, is power in minus power going to the load. And we can write it in equation form this way, that PD is voltage regulated into IL minus voltage to the power dissipated load, which is VL into IL. Now I've said here that from this last equation here, equation 4, if the unregulated input voltage is subject to large variations, then the worst case is used to compute the power dissipation of the, it should be of the devices, power dissipation of the devices. Okay, so supposing the input, supposing you're designing a power supply with the output voltage was 10, but the unregulated voltage is maybe varies from maybe 12 volts to 20 volts inside. So the input voltage varies from maybe 12 volts to 20 volts. Your design voltage is 10 volts. Then when you're designing for the devices, the semiconductors, you must consider the worst case. The worst case is when the input voltage is maximum. Okay, the input voltage is maximum. Okay, so that from the data sheet of the devices, your transistors, your op-amps must be able to handle the worst case. In this case, it is 20 volts. I hope that is understood. If you put a transistor which can only block maybe 15 volts, when the input voltage rises to 20 volts, it's going to destroy that semiconductor. Okay, we saw some data sheets of op-amps of National Semiconductor 741. Remember, this is what I'm saying. If you look at this circuit over here, we're considering this circuit over here. So if the input voltage V1 ranges, let's assume the design voltage V0, the design voltage is equal to 10 volts. Maybe he'll be at 10 amps. And the input, you're told, can vary. Let me give a practical case, maybe from 15 volts all the way to maybe 40 volts. You got an unstable power supply coming to your thing. Then what I'm saying is that if you look at the voltage side of things, first of all, remember this op-amp is normally connected. It's normally connected to the power supply. And we saw for the national semiconductor, you can connect maybe minus V, the maximum voltage across the op-amp was maybe positive 18 and minus 18. So means the peak voltage between the positive VCC and minus VCC is 18 times 2, which is 36 volts. So for example, in this problem over here, where the input voltage can go up to 40 volts, it means it's going to destroy the op-amp. Okay, you have to get an op-amp which can handle that 40 volts. Okay, 40 volts means minus 20 plus 20. Okay, so maybe the top side, you can put a Zener, which is fixed, but I don't want to waste time on that right now. What I'm trying to say is that the 40 volts going to the op-amp, you can put maybe a Zener, which is say 15 volts Zener. So this goes to your 40 volts. And this will have to go to the 0. If you had a 0, then this will clamp this voltage to maximum 15, and this 15 can go to the positive of the op-amp, which is your plus VCC. And then you'll need another Zener, which will go to the 0, and this one will also drop 15 volts. So when the voltage passes 40, your op-amp still sees a maximum of plus minus 15 volts. Okay, but for you people, the problem will not be so complicated. It will be simple, like the one drawn in the diagram over here. So if you're given a problem and you're told the input will vary from 15 to 40, we can assume that the op-amp that is drawn in the diagram can be subjected to plus minus 20 volts, unless the question says otherwise. Now, the other problem is that the transistors Q2 and Q1 must be able to block these 40 volts. They must be able to operate properly with 40 volts between its collector and the emitter. Okay. So if you use a transistor which VCE max is 30 volts, Then if your regulator gives a lower voltage, for example, in the case the load is short-circuited, so that the output voltage is almost zero, then it means the full voltage of about 40 volts is applied across the transistor Q1, and the full voltage minus VBE Q1 is applied across the collector and emitter of Q2. So for example, in this diagram, the voltage across here will be VI minus VL, the voltage between here and here. And for this other second transistor here, the voltage between these 2 points will be VI minus, into brackets, let's call this VBE 1 and call this one VBE 2. So it will be VL plus VBE 1. Okay, but normally in a practical we don't just design exactly, because VBE is approximately 0.6 or 0.7. Normally in a practical design, we normally use what are known as safety factors. So for example, in this problem where I tell you the maximum unregulated voltage is 40 volts, I don't go and pick transistors which can operate well with VCE equals 40 volts. I'm going to put a safety factor. Okay, so for safety, you go and pick a transistor which can at least block 50 volts or 60 volts. Okay, so there's a safety factor, there's a safety margin, so that your circuit becomes reliable. Okay, so let's continue. So we're talking about dissipation in our regulator. This dissipation gives rise to inefficiency in our regulator. Now, efficiency of the regulator is defined as power going to the load over power entering the regulator times 100%. So in formula form, it's just PL over Pin times 100. But PL is the voltage across the load, current across the load, and Pin is the maximum unregulated input. So in that case, where the example, the input can vary from, I think I wrote something to 40 volts. If it was 15 to 40, you put 15 over here, the maximum value. So it's PLIL divided by the power input, which is the unregulated voltage, the maximum unregulated voltage into IL, and this IL will cancel, and you just get VL over V unregulated times 100. Okay, so that's the other important parameter of a regulator. Now, the advantages of a series regulator is that they are cheap and simple to implement. This design also lends itself to IC fabrication. Remember, in the last class, we were looking at some of the regulators made by National Semiconductor, like the LM. National can see the LM, and it's 70, I think 7405. And I think there's 74, 012. There's so many of them. There's so many of them. So the 7405 will be a 5 volts regulator in form of an IC chip. 74012 will be a 12 volt regulator. So when you want a very cheap regulator, instead of building it out of transistors, you just buy these chips. In fact, you can just go to the internet and see a few of them, because you need them for your projects. So you can see many of them over here, like this Texas Instruments. Oh, so it was not LM. I thought LM is Texas Instrument. Let's see. Okay, let's go to this. I think Mauser, they sell the chips from different companies. Let's go to Texas Instrument and see. I'm getting out of Texas Instrument. I want the LM series. Let me just search with IC. Regulators. Yeah, these are the series I was looking for. So this you see, these are the common ones like this LM705 5-volt regulators. Then we have 12-volt regulators. I just want to confirm this LM. I thought it was, or is this National Semiconductor? Let me just go to one of these and look at the company. This is a marketing company. What you can see, you're given the data sheets, some technical information, LM705, which is a 7-volt minimum voltage, 7 volts input, maximum voltage, maximum input voltage is 35, and this one can only supply a maximum of 1 amp. And the minimum output voltage is 5.2. Sorry, maximum output voltage is 5.2. Minimum output voltage is that. No, I wanted a company that manufactures this, not this. It's giving a name that I do not know here. CDIL. Unless CDIL bought this, but normally various companies tend to manufacture these regulators. But let me use LM here. LM. And still CDIL. I don't know which company this is. Because LM series I used to know, unless National Semiconductor collapsed. Let me just search with this one. National Semi. It looks like National Semiconductor is no longer there. But it's here. National Semiconductor. Because this is a company I used to know, used to manufacture these ICs. And that's still the National Semiconductor. So you get more details from them. So most of the digital boards we have inside the labs, the companies that fabricate those digital boards or lab kits, they just go to this, order these IC chips from these companies. And you see in National Semiconductor, there's the LM78. Then they normally use 78 series. 7805 is 5 volts. 7812C is 12 volts. 7815 is 15 volts. So they'll show you how they're packaged. They're in TO3 packaging, this metal package, or this one is called T20, the one, the plastic with the metal behind. Okay, so if you go to the manufacturer, they're going to show you the internals. Okay, so for us, we want to go very deep, but we could have gone deep if we had time. Okay, so if you look at the inside, you can see this is the output. The output is here. And you can see they're using a Darlington. Q15, Q16 is the Darlington output. Okay, this Q14 is your short circuit protection. So that when they drop across this R16 is approximately 0.6, this will switch on and cut the drive to Q15. It will like short circuit. So there'll be a little drive current. And this Q11 is driven by a differential amplifier here made of Q1 and Q16. So there's not a lot of time to go through everything. Okay, but just remember, what is happening here is that we got an error amplifier, we got a reference. So you can see the reference is this diode D1, 6.3 volts. And the base of Q13 and Q14 form the driving circuit of a differential amplifier, which is formed by Q1 and Q6. Won't go so much into the internal details of the workings of this, but I just wanted to show you. Inside here, you got the output stage, which is Q5, Q6. You got a reference, which is D1. And the rest of the circuitry is for short circuit protection and your error amplifier. Okay. So if you go to the internals of this, because this is the manufacturer, he's going to give you lots of details, technical data. So they've got all the 5 volts, 12 volts, 15 volts all lined up, the maximum output voltage over there, and the minimum. And then they'll give you the maximum, what's the maximum input voltage? They give you details of the minimum input voltage for good regulation. So for the 5 volts, you got 7.5 volts. 12 volts, the minimum voltage is 14.6. And for 15 volts, the minimum voltage required is 17 volts supply. And they give you data about its dissipation, etc., etc. And pick on the ripple voltage. Okay, we'll stop there for now. Now we'll stop. What I'm showing you right now, we'll continue the class notes. So it was for National Semiconductor. It was not 74, it was 78. So these are, and the other 78, 015. Okay, so you can see just a small chip. It looks like a power transistor, and they're not too very expensive. Now the disadvantage of these series regulators is number one, or A, in high power applications, the voltage drop across the control element gives rise to losses and results in low efficiency. So if you want high efficiency, the voltage, your design voltage output should be close to the maximum, should be close to the input voltage and related input voltage if you want high efficiency. That's what that means. And B, the output must always be lower than the input voltage. Of course, for the current to flow from the through the transistors, through the power transistors or the control element, the input voltage must be greater. Remember, with the power transistors, of course, most of the time, this transistor over here, Q1 over here, when the transistor is completely on, for a silicon transistor, we call this voltage VCE set, which is typically 0.2 volts. Typically 0.2 volts. So even though the transistor is completely on, approximately 0.2 volts would be lost across this transistor. And that's what we mean. So apart from its minimum operating voltage, you got to ensure that your design voltage plus 0.2 volts across this transistor must equal to the minimum power supply and related voltage. Okay. So let's do these simple questions over here quickly. Then we'll do a simple exam problem. So questions on this topic: list the schemes used to implement DC regulators for 3 marks. The schemes are series, shunt, and switch mode. Switch mode, I told you that's your assignment. Go and look at the problems. The book to use is Professor Sen, Power Electronics by Professor Sen. I think you can get them in the internet. Me, I bought mine from the library. Sorry, from the university bookshop. Part B, using a block diagram, explain the principle of operation of the above-mentioned regulators. So that's in your notes. Part C, the regulator in the figure below is designed to give a load current of 2 amps from an regulated power supply. Vin varies from 15 to 40 volts. Evaluate the output voltage, given that the op-amp has got a gain of 100,000. VB Q1, Q2 is 0.65 volts when operating in the active regions. Then briefly explain the possible cause of error in the computation. The solution is very easy. We've done the solution over here. Accurately, V naught this is a type. There seems to be a typing error here. From this equation 8, let's just do it by hand here. From equation 8, V naught is AD, VZ by that. So if you divide by AD, V naught will be VZ minus 2 VBE over AD all over 1 plus beta, where you know beta is R2 over R1 plus R2. So I don't know what they're typing. There's a typing error over there, which I won't edit right now, but what I've written there is, and we're saying this is normally approximately, V naught, it's normally approximately Vz into 1 plus beta. Vz is approximately 1 plus beta. So if beta greater than 1, you can also say it's approximately Vz over beta.
Excuse.
Yes? Continue.
I think your final derivation was correct. Like when you said that d is much greater than 1, so the denominator will just be beta over.
Oh yeah, this AD,
Just
sorry, this, yeah, thank you. This one is supposed to be this one over AD. So this one is 0. So this one should not be there. Okay, so Z is just that. So we just use the values. What values are we given here? So you can see here, told AD is 100,000. And where's the circuit? Where's the circuit? Oh, the circuit is down here. Okay, the circuit is down here. So we are told V naught is Vz over beta. And you know beta is R2 over R1 plus R2. And you're told that AD is 100,000. So this is just simple substitution. Just simple substitution. So in this case here, beta is equal to 12K over 12K plus 12K, which is 1/2. Okay, so V naught is just simply 2Vz, and Vz is 4.7. So this 1489. So it's so easy. Now let's do this other part, which I'm sure most people who just cram might not be able to get. So briefly explain possible causes of error in this computation. What are the possible causes of error in this computation? What are the possible causes of error in this computation? Error number 1 is the tolerances of the resistors. From your first year measurements, you were told resistors, the color bands, the first color, the second color, the third color, and then the fourth color gives you the tolerance of the resistor. So it's impossible to manufacture resistance of exactly 12K, 12K. So it will be maybe 12K plus or minus 5% if it's got a gold band resistor. So all the solutions, we're not taking it into consideration the tolerance into which the manufacturer can manufacture these resistors. The other one is, remember, VBE is a function of temperature. VBE is a function of temperature. So as the temperature increases, the VBE decreases. Okay, so if you don't take care of the heat sinking of your transistors, the temperature will vary a bit. Similarly, for your Zener diode, it might be affected very slightly by temperature changes because it's a diode. So those are some of the things that you got to take into consideration. You might design it very well. It works in a computer simulation exactly. You get 9.4 volts. But now when you go to the lab to manufacture the real thing with real components, you find it's not the case. Now, let me go and look. Now, let's do this one. Let's do this one. Now, this is a slight modification of the circuit that we just designed, which includes this other transistor over here. Now, this transistor is similar to what I showed you in that op-amp, the 745C from National Semiconductor. This is to prevent short circuiting of our transistors Q1. Or if this is a transistor Darlington, means there are two transistors in one. It prevents the blowing up of these two transistors if somebody accidentally short circuits the output. So for this one, the design voltage is also approximately V0 is equal to Vz by beta, approximately, where beta in this case is Vz. Beta in this case is what? 5K over 5K plus 10K, which is 15K. So this is the same as 1 by 3. So in this circuit over here, V0 will be 3 Vz, which will be 3. Vz is 4.7. 4.7, which is 21, 12, 14. So for this circuit, the design voltage is 14.1 volts. Now the function of this transistor, let's call this transistor T3. Because we have T2, or then let's call it T3. So the function of this transistor is similar to what I showed you in the IC chip from National Semiconductor. When the voltage across, when current starts to flow to the load, this side of RCS, I've written R, capital R means is a resistance, small c is short circuit. It's for short circuit protection. So when this voltage reaches the cut-in voltage, which is normally about 0.6 volts, then this transistor T3 will be turned on and it will branch the driving current. So this current, which comes here, let's call it I op-amp, it will start branching the current this way, and therefore it will protect, it will decrease the drive current to Q2 and also Q1, and hence when RCS times the current, which is IL, going towards the load, L will be going towards your load over here. These other currents are negligible. The currents passing, these biasing currents passing through the 10K is negligible compared to the currents going to the load. So times IL is equal to 0.6. Then we've reached our short circuit, our maximum high load current, because the short circuit protection will start being active. So for this circuit, IL max will be equal to 0.6 volts. divided by RCS. So for example, if RCS is 0.1 ohm, then the short circuit current will be 0.6 divided by 0.1, which is 6 amps. So that's the function of this circuit over here, comprising of the resistor RCS connected between the emitter and collector of T3. It's there to provide short circuit protection of the circuit. So especially most of the lab equipment, that's what they use, because they know some students are going to accidentally short circuit the output of the power supply. So to prevent the transistors blowing up all the time, they use short circuit protection. And now, do you have another class after this? I wanted to do an exam problem based on this one. Moses, do you have any after this?
The light blue.
You can do the example.
Huh?
You can do the example.
Yeah. So basically, in the exam, let me see. Even CAT, let me just check my notes over here. Okay. I'll open this CAT and see. So CAT exams, they're just almost the same. So this question is on regulators. Create the blocks that constitute a closed-loop regulator, clearly explaining their functions, and hence explain the principle of operation of the series regulator. List the advantages and disadvantages of the series regulator over the shunt regulator. So we've done that. Then part B, the regulator of figure 3 is required to supply a nominal load current of 5 amps from an input that varies from 20 to 45 volts. Okay, evaluate the output voltage of the op-amp. Sorry, evaluate the output voltage given that the op-amp has an open loop gain of 100,000 and the transistors has got a VBE of 0.6 volts. So that's easy. We've already done a similar one. Then part C, given that the transistors have an HFE of 100, design requirements, or maybe more correction, read design the requirements of both the transistor if the op-amp has a maximum drive capability of 10 milliamps. Calculate the dissipation requirements of the Zener and the transistors. What is the maximum efficiency of the regulator? And state any assumptions used. Draw a modified circuit with your circuit protection at 5 amps. So this is the equation. So, and the circuit, I think you are given here. It's here. The circuit is here. So I can't pick it alone. I think you're told to use the bold letters. Okay. I'll start with the circuit. What is this? Document 1, okay. So, okay, I just wanted the question to be in front of us. Oh, what's wrong with this thing? So I'll do the part C, because here's where most students get a problem. Here's where most students get the problem. So part B, we have already just done. The output voltage we note is just Vz divided by beta. In this case, beta will be 4.7K divided by 4.7K plus 10K. That was just easy 5 marks. I don't know why you people fail. Okay, let's do the second part. Given that the transistors have got a HFE of 100, design the requirements for both of the transistors. Okay, if the op-amp has got a maximum drive capability of 10 milliamps. Okay, then calculate the dissipation requirements of the Zener. Then you ask, what is the maximum efficiency? Okay, so let's start with the requirements of the transistor. So for that, first of all, we got to find out the output voltage. So let's find out the output voltage. So for this circuit, V0, we found was equal to Vz divided by beta, where beta is equal to, in general, it's R2 over R1 plus R2 plus R2. And that is equal to 4.7. I'll just use the K over 4.7 plus 10. So you can say that beta is equal to 4.7 over 14.7. Okay, and therefore V0 will be Vz, which is 4.7 volts times 14.7 over 4.7. Oh, my calculator is next to me, but it's dead. So I'll have to use Microsoft's calculator. It's 4.7 times 14.7 divide 4.7. So it's 14.7 volts. So I'll just check. Somebody can check that I'm not done a mistake. Let me see if my calculator will work. 4.7 times 14.7 divided 4.7. Oh, but the 4.7 will cancel. This one is obvious. I don't need a calculator. This 4.7 is the same as this one. So it's just 14.7. Okay. So we've gotten our output voltage. So we need to design for the power. Let's consider this top transistor Q1 and this bottom transistor Q2. So we go to design for the power dissipation of Q1. So let's find out the collector currents of Q1 and Q2. So IC Q1 will be equal to what? And IC Q2, the collector current of Q2. Now for our system, it was designed to supply 5 amps. So IC Q1 is 5 amps. And IC Q2 will be 5 amps divided by HFE Q1. And you are told that if the transistors have got a gain of 100, so ICQ2 will be 5 amps divided by 100. So we've gotten the currents that are flowing through these two transistors when it's delivering. When it's delivering 5 amps to the load. When it's delivering 5 amps to the load. So let's get the power dissipation of Q1. So we can write PD Q1. This is at maximum load. Will be IL times VCE of Q1. And IL is 5 amps. VCE Q1 is Vn minus VL. So this is 5 amps. Vn maximum is 45 volts. Minus VL. Our load voltage, we found it, be 14.7. Let me try my calculator again. 45 minus 14.7, 30.3. 30.3 volts and 5 amps. So this is 151.5 watts. So since this is a theoretical problem, and that's the solution. But if this was your project in the lab to design this power supply, you cannot go to the shop and buy a transistor which is rated 1.5 watts. You want to get it first of all, like the 2N3055 we saw last time. It could dissipate 115 watts. In fact, that's the most common transistor that is used in the lab power supplies. And that was rated, I think, at I think it was 115 watts. It was rated at 115 watts. It was rated at 115 watts at 25 degrees centigrade. So if you go to the shop and buy and put that transistor inside this circuit, it's going to burn. Okay. So what you can do, if it was a practical problem, not an exam question, if it was like a project you're doing in the lab, then you'd have to put 2 of those transistors in parallel for it to work. You'll have to connect the outputs of like those 2 N3055 in parallel, like that. And here's where you give your driver. So each can handle 115 watts at 25 degrees centigrade. So here now you got a total of 230 watts at 25 degrees centigrade. Then you design a heat sink, which will maintain a temperature close to 25 degrees centigrade. But since this is a theoretical exam problem, that's the power dissipation of the transistor required, 151 watts. So next, let's find the power dissipation required of transistor Q2. So PD Q2 at maximum load will be equal to IC Q2 times VCE Q2. Now remember, IC Q2, we got it at 5 amps divided by HFE1, and you're told HFE of Q1 is 500. So it's 5 amps divided by 100. So this one, nobody gets it right in my exam questions. So this is 5 amps divided by 100. And then VCE Q2 will be equal to Vin minus the voltage across VCE of the second transistor is the base voltage of Q1, which is VL plus VBE of Q1. And the VBEs we are told to take 0.6. So it will be minus V0 or VL plus 0.6. That's in volts. And V0 was 14.7. So this will be 5 amps divided by 100 HFE into Vin. What was Vin? Was it 40? I'm forgetting it. 45. Vin is 45 minus VL 14.7 plus 0.6. That is 14.7 plus 0.6, 15.3. So this bracket, square bracket, is 15.3 volts. and the output is in amps. So this will be 5 amps times 15.3 divided by 100. And the power you get is 0.765 watts. Okay, so the minimum requirement of...
Excuse.
Yes?
I think we are not solved using the 45.
There's a problem with the 45 minus 0.7. I'm using my calculator, which is misbehaving. Let me try again. But you didn't tell me the problem. You should have told me what the problem is. Okay, let me... okay. I think I know what the problem is. Okay, thank you. I think I know what the problem is. I think I just put 14.7 plus 0.6, 15.3. Okay, so this is one which is 15.3. So in this square bracket, I should get 45 minus 15.3 volts. 45 minus 15.3. Yeah, 29.5. Okay. So is that okay again? What's the problem now again? Have I done a mistake again? Omola,
27.
it's 27.
29.7.
Oh, I was in my calculator. I've typed 15.5. Okay, okay. In my calculator, I've punched 15.5. That's what the problem is. That is what the problem is. Okay, let me start again. This calculator of mine, it's very unreliable. It's over 20 years old, so minus 15.3, 29.7. Okay, so let's multiply the numerators. 5 times 29.7 divided by 100. 1.45. Sorry, 1.485 watts. So the dissipation requirements of the second transistor is 1.485 watts. So there are many transistors which can easily dissipate that amount of power. But just be careful if you are doing it in a practical lab environment. In theory or in your simulators, you can't blow up transistors in your computer. But when you're doing it practically, they'll blow up and you just see blue smoke coming out of them. So for this one, there are so many transistors we can handle that. But for this question, the answer is 1.485 watts. That's the design requirement. And the next question was what? Next question, dissipation of the Zener diode. And then minimum efficiency of the regulator. The dissipation of the Zener diode is very easy. And some of you don't even get it right, and it's so easy. So I'll just write it here on this space here. So dissipation of Zener I'll use that Z. It's just IZ into VZ. Now, even this one, some of you get confused. Let's look at the circuit. There is the circuit. What is IZ? So you got to consider the worst case. You're told the input voltage can vary from 20 to 45 volts. So when the input voltage is 20, then the current that will flow through this 6.6K, which is the same current that will flow through the Zener, it will just be 20 minus VZ divided by 6.6. But that's not the worst case. The highest current will flow when this voltage is 45. So it's 6.8K, 6.6 or 6.6K, 6.6K. So VZ, the worst voltage was what, 45 or 40? Let me just see again. 45. So the current will be 45 minus Zener voltage. My memory is becoming very little now. 4.7. The units of the distance voltage. Oh, is it 6.6? You guys have got good eyes. According to me, it looks like 6.6 into VZ, which is 4.7 volts. So the units here are milliamps because I'm using K, 6.6K. So Omola, open your calculator and show me if I'm going wrong. I'm using an old calculator here. So 45 minus 4.7, that gives me 40.3. So for the square bracket, I'm getting, in the numerator, I'm getting 40.3 divided by 6.6K times 4.7. So I'll get 40.3 divided by 6.6 times 4.7. So I'm getting 28.69 milliwatts. So power dissipation of Zener is 28.69 milliwatts. So that's very easy marks. Normally I just give 2 marks for 1 mark for the answer, 1 mark for the process of how you arrived at the answer. Those are 2 easy marks. 2 easy marks. And then the last part of the equation, calculate the dissipation of the Zener and the transistors we've done. Then you're told what's the maximum efficiency of the regulator. And then draw a modified circuit. It should circuit protection at 5 amps. So I think what is remaining is maximum efficiency. So I'll have to rub these top ones, which we just done. Because if I open a new page, I'm wasting time shifting back and forth to get the equation. Okay. So efficiency. So nita is P to load over power in times 100% efficiency in percentage. So what's the minimum efficiency? Okay, if you're looking for minimum efficiency. So when is the circuit most inefficient? Now P load is IL into VL, and Pin is IL to Vn max for minimum efficiency. Remember this Vn ranges, I think, from 45 volts. Was it 20 to 45? Let me just check again. 20 to 45, yes. So this ranges from 20 to 45 volts. So in percentage times 100. So when Vn is maximum, this number is minimum. So IL will cancel. So VL was 14.7 volts, I think, over the maximum, which is 45 volts times 100. Let's just check what the output voltage of V0 is. 14.7 volts. So we just divide 14.7 divided by 45, which is 0.32. This will be 0.327 times 100. And this is 32%. As the minimum efficiency. To get the maximum efficiency, you just change the in max to be 20 volts. So the maximum efficiency will be 14.7. It can be 14.7 divided by 20 volts times 100. This is nita max. So if your input supply is small, close to the design requirements, you'll get maximum efficiency, 14.7 divided by 20. And that is working to be 73.35%. And so that's how you get the efficiency, very easy max. And then finally, we are told to modify the circuit to include short circuit protection. So I've already shown you a circuit in the problems, how to include short circuit protection. So we've gotten the minimum efficiency of the regulator, then state any assumptions used. What are some of the assumptions used? I'll leave it for you to think. What are some of the assumptions we've done? Of course, we are assuming a dealer pump. We are assuming that the power going into the input circuit through the 6.6K is not being calculated. The power going through the 10K and 4.7K is not being calculated. We are assuming that the collector current of Q1 is only IL. But practically, the collector current is actually IL plus the current that passes through this 10K and the current that passes through the 4.7K, although this is normally negligible because when you have to calculate, this is 10K plus plus 4.7K, that is 14.7K. That's 14.7K. And if the design voltage is 14.7, means only 1 milliamp. 1 milliamp is flowing over here. but we're designing at 5,000 milliamps. So this 1 milliamp is negligible compared to the 5,000 milliamps going to the load. So those are some of the simple assumptions we've made. Okay. So then you're told to draw a modified circuit with short circuit protection at 5 amps. And so we'll just go back to this circuit over here. Get the rubber over here. There's somebody who's trying to get in Moses, but I won't allow him in because he's coming after half an hour, 1 hour and something. So you just have to draw your transistor over here. Include a resistor over here, the base here. So this should be NPN, and this is what we're calling an RCS. So RCS times 5 amps should equal to 0.6 volts, which is the cut-in voltage. And this implies that RCS is equal to 0.6 divided by 5, which is 0.12 ohms. So you design for RCS is 0.12 ohms, 0.12 ohms. So everybody is leaving the class. What's happening? I only seen 32 people. Moses, what's happening? Okay, for those of you who are there, go and try this problem. Are you people there? Or you one left? I'm seeing 32 people, but
Yes, we are.
Okay, do this problem. This problem came to my exam when I was a 50th student outside. It made us sweat in the exam. So let's see if Nairobi University students can do it. Moses, I hope you don't have a class after this. Do you have a class after this? So this is a problem that came when I was a student on series regulator.
I don't know, the light group got a telecom class. I don't know if it's still there today or not.
There are many. Okay, if you do this one, you'll get 100 out of 100 in the exam. Oh. The pen is low, but I've got another pen. So in this circuit, you're told the input varies from 37 volts to 7 volts. And you're told to find out the range of output voltages. Now, this is a variable regulator. There's a 500 ohm port, which can vary. So remember R2, when the port is on top, will be 1K plus 500 ohms. R2, when the port is at the bottom, will just be 1K. Sorry, R1 will just be 1K. R2, in that case, will be 4.7K plus 500 ohms. So find out V naught. Or the range of V naught. Find out the range of V naught. In this case. Now, if you look at the transistor to the extreme left, you're also told to find the current through the transistors when the output voltage is 30 volts. Well, current through the circuits when V naught is 30 volts. And if you are tough, you can also find out what is SV, the stability factor of the output voltage, which is defined as delta V naught over delta VI. If you can do that, then you'll get 100 out of 100 in the exam. Now, let me see if I can give you some more information. In my exam, I was also told to find out what is R naught, which is the resistance in looking back. R naught is the resistance that the load sees. So I'll just give you a hint of how to tackle this problem. You can start with so there'll be two cases when this potentiometer, let's start with the easy one, when it is at the bottom. So when this potentiometer is at the bottom over here, then you can use this path all that way and call this voltage V naught. So the first equation you'll write, now IN755 rather. Oh, my eyes are no. It's IN753. How come I don't have the data over here? Let's go to the internet. I don't have it in here. So when the Zena, IN 753. So this is 6.2. So you write down. It is a 6.2 volts, 400 milliwatt Zener. 6.2 volts, 400 milliwatts Zener. Then let's look for the next one, which is IN746. It looks to be a 3.3 volts, 400 milliwatts Zener. Can you see the beauty of the dynamic resistances? IN746, 746. And it's a 3.3 volts. So 3.3 volts, 400 millivolts. Okay. Which are the Zener? We got only two Zeners. So let's look at the important transistors there. We got the power transistor 2N 149. It is not a MOSFET. So this is a power transistor. It's an NPN. It's a 40 watt. Steve. Yeah, Steve. Okay, niko kwa klasi bwana. Kesho. Sorry for that interruption. The 2N sorry, it's 2N 1049. This one is 40 watts, 80 volts maximum. What's the current? And HFE. So HFE mean is 30. These are the important parameters. And IC max there is 8 amps. So the maximum current that can flow through it is 8 amps. And then the next transistor you're given is 2N 56. 2N656. So this is a 1 watt transistor, 60 volts. IC max is 0.5 amps. HFE 30. And the last transistor is 2N. Is 2N 338. So this is a 30 volts transistor. So VC max is 30 volts. Maximum collector current is only 20 milliamps. HFE is 45. I think that's all the data that we need. The power dissipation maximum is 0.125 watts or 125 milliwatts. Okay, so let's go back to our class. So just write the data. So for these zeros, I'll just write the data 753. So this Zeno is 6.2 volts. I just write here 6.2 volts. 400 milliwatts Zener, and the other Zener 746. This is 3.3 volts. 8.3 volts, 400 milliwatts Zener. Then for the transistors, 2N1049 is which one? Or the top one. So the top one, so this is a 40 watts. I think that is going to become so messy. Let me just write them down, the data down under here for you to copy. So this is the data. So for the 2N1049, this is 40 watts. Maximum dissipation, so that would be at 25 degrees. VCE max would be 80 volts. IC max is 8 amps. It's 30. So maybe I'll just put a column for that. And the next transistor was 2N65. 656, 2N656. 2N656. This one is a 1 watt. So 60 volts. This max is 0.5 amps. FEE30. And then the 2N 338. PD max is 125 milliwatts. VCE max was 30 volts. IC max is 20 milliamps. HFE 45. Okay, so you can copy that data. Then I was going to give you a method of okay, let me just leave it there. So I hope everybody has taken. If you're not taken, please taken the data. So I'll give you a hint on how to obtain the output voltage. Okay, so let's start. Let me give you a hint of how to get the output voltage from this side. So use KVL over this pink path over here. Okay. Let's name these transistors so that let's call this top transistor Q1, this one Q2, and this one Q3. And this pre-regulation transistor, we call it Q4. Now, for those of you who are smart, you can see that Q4 is just actually a constant current source. Q4 is just a constant current source. It ensures that this current over here, I'll call it I Q4, is equal to a constant. Okay, so let's start. I didn't know I drew the line so big. Let me remove some of these columns of these lines. And when I remove it, they all come out. Okay, it doesn't matter. Okay, let's start solution for V naught. So let's apply KVL. From ground or 0 volts through 6.3 volts Zener base of Q2, sorry, of Q3 to V naught. So basically what I'm saying, I'm using this path over here. I'm starting here. I'm going through this Zener, 6.3 volt Zener. I'm going through the base of this Q3. I'm going to this potentiometer, 500 ohms. So for the first part, I'll use the potentiometer at the bottom point, at the bottom of 1K. Then I go through the 4.7K, I go to V naught. So let's do that. So if we do that, I'll get that 6.2 volts. That's the voltage of the Zener, plus VBE of Q3, plus the drop, at the base, because the base, the potentiometer initially will be at the 1K point, the top of the 1K point. So what is the drop? Remember this top resistance, we are calling it R2, and the bottom resistance, we are calling it R1. So it will be the drop across R2. Let me first of all just write it as R2 plus R2 over R1 plus R2 into V naught should equal, yes?
I'm requesting to be let out of class while so another committee. So
Okay. Okay, just take down the question. I'll just finishing. I'll just finishing for you people. So this should be equal to V naught. So if you get that, resolve V naught. That's the first important point. The next important point is IQ4. IQ4 here is actually a constant current. So IQ4 or you can call it ICQ4 will be VZ minus VBE of Q4 over RE of Q4, which is 1K. And this is IN746 at 3.3 volts Zin. And you can use 0.6 as your active voltage for the thing. So over 1K. So this is VZ, 3.3 and 0.6 over 1K. So this will be in milliamps. So this is your constant current. Okay, so that will be the supply current. So this supply current over here, this supply current over here, some of it is going to be divided down to Q3, some of it is going to be driven to the base of Q2. Now, if you know that, then in fact, the answer, you just solve this one, the answer. Use VBE to be equal to 0.6. VB 0.6. It is the last part, the part 2, the resistance in looking means the resistance, the source resistance of your regulator. Okay, the source resistance of your regulator. Any questions on this? So that is what I was tested with when I was a fifth year student. And we had to find out what is SV of the circuit, what is the resistance in looking back of this voltage regulator. Everybody has taken. Eyes close. Let me put back the solution back here. So series regulators is the simplest. When you're going to exam, start problems with series regulator. That's the simplest. Then the next simple one is what? Multipliers and switching regulators. Yeah, once you understand them, they're very simple. The most yes is amplifier. Most yes is chopper amplifiers. So got to do a lot of calculations in the case of the chopper amplifiers. Okay, so thank you, everybody. Thank you, everybody, those who are there. So if you've got friends in, is it power? You better tell them, help them to do this. They shouldn't fear if they see strange problems. Op-amps are simple. There are so many assumptions using op-amps. We didn't consider things like the drift voltages inside the op-amps, inside regulators. We always assume that the ideal output is equal to AD into the difference between the two inputs. But practical op-amps, they'll give you a lot of problems if you do them in the labs because of the offset voltages. Okay, so thank you. Unless anybody has got a question, you can switch on your mic and tell me before I close. Okay, so I'm closing.
Yes.
Yes,
Was the discussion of the CAT settled?
Pan? You ask the CR. Why are you asking me? If I said my CR, I would like my CR to be on Monday. If that was me. How many people agree on Monday? Because with me, I want to rest during December. I don't want to be thinking about CR. Do you all agree we do on Monday?
No, no.
No, but
The CAT is
Moses. No. Moses told me next year. I communicate with Moses, yes, yeah. Okay, so you go and ask Moses. It's not finalized, in fact, the date even in January. Because me, I wanted to finish my CATs this week. Is that okay, Mirago?
yes.
Okay. Okay, thank you then.